Picture looks like this, and what we want to do is have GeoGebra draw a circle. Basically, I'm going to have it draw the unit circle because I think it said that somewhere. They say a circle, any circle of radius 1 would do, but I'll go with the unit circle centered at the origin. And I'm going to indicate points, have GeoGebra plot the points, and also a point up here. So if this is the unit circle, then what would be the equation of the circle centered at the origin whose radius length is 1? You can type in a lot of cases where it's not too terribly complicated, a literal equation like x squared plus y squared equals 1, and GeoGebra will be able to figure that out. Standard conic sections it can figure out and graph that for you. So we'll have it graph x squared plus y squared equals 1. This is the point 0, 1 right at the top of that circle. And then I want to express the other points so that, and you can see what's going on with this rectangle. Basically, the value of h and the value of b are flexible and depend on each other, but they also depend mutually on the 4 points right there. So what I want to do is define all 4 of those points in terms of a single variable t. If you think of the way the cosine and sine functions are defined in unit circle trigonometry, we can define them all in terms of t. Basically, we're sitting on the unit circle. So this point, if we let t maybe take on values from 0, like from 0 up to pi over 2, then this could be cosine t, sine t. Now, I only teach trigonometry about every 10 years. I taught it in 1994 and then again in 2004, and maybe I'll teach it again in another couple of years, I don't know. But is this the way that cosine and sine are defined after you do the side opposite over hypotenuse and all that? Okay, so you can see that. Now, this is cosine t, sine t. Well, if you reflect that point about the y-axis, you get negative cosine t, sine t, like that. Just change the sign of the x-coordinate. If you reflect it about the x-axis, that changes the sign of the y-coordinate, like that. And if you reflect it about the origin, it changes the signs of both coordinates. So negative cosine t, negative sine t. So if we define all 4 of these points in terms of these coordinates, and then we take a slider with values of t and let it slide back and forth between 0 and pi over 2, then all 4 of those points will move and will give us a rectangle. Now, what GeoGebra will do, it will graph this polygon, and it will keep track of the lengths of all 4 sides as well as the area of the enclosed region. And we don't have to define the area formula. I'll also have it graph this triangle, because looking at the problem, for what value of h and b do the rectangle and triangle have the same area? Well, the way this picture is drawn, it looks like the rectangle has way more area than the triangle. But if we slide the value of t probably down toward 0, I would think, then the rectangle will get skinnier and the triangle will have a greater height and I guess also even a greater base. And at some point they'll have the same area. What we could even do is have it display the area of the triangle and the area of the rectangle kind of in real time as we do this, and just kind of do this and slide the slider until they agree. So that's kind of the plan. Now let's see if I can make it do it. Hope so. All right. So we're going to begin with just typing in x squared plus y squared equals 1, and it ought to be able to give us the unit circle. X squared, so down in the input box, plus y squared equals 1, and it graphs the unit circle. I'd like that to occupy a bigger portion of the screen because that's where all the action is in this particular problem. So I'm going to click up here on the graphics view button, and that'll give me some options. Actually, I'm going to click on the little down arrow. Now, there's one version of GeoGebra, I think this might be one of the new ones, where it looks a little different up here. Some of the worksheets had this and some didn't that I saw that were turned in. If you click the down arrow, There's probably another way to get to zoom in if you don't click that, but I'm going to click that and click zoom in. You can also manually adjust the X-min and X-max and Y-min and Y-max. If you right-click and go to graphics, if you go to graphics, then I should be able to manually adjust that. But I'm just going to click zoom out, zoom in a little bit more, and a little bit more. Okay, that's good. Now, 4 points. Now, points, what we could do to plot points is go here with this button and just type on the screen. I usually have a hard time getting them exactly where I want. And really, I want to specify the X and Y coordinates in terms of the slider T. So I'm going to type in the ordered pairs explicitly in terms of T, but GeoGebra will get confused if it doesn't know what T is. So first, the slider. A slider is key. That's one of the items on the rubric that I've specified that I want to see in every worksheet. Where it says A equals 2, here's slider. There are various features on this particular button, but number 1 is slider, so I'm just going to click there, and then click anywhere on the screen, wherever you want the slider to be. I'm going to click right over here, and there we go. Let's call it T, because that's going to be the variable. You could call it, let it be anything, though. I wanted to go from 0 to about pi over 2, about 1.57. You take pi over 2 and round it somewhere, so I'm going to say about 1.57. And as far as the increment goes, I'm not sure. Let's go with 0.001. There. Now nothing happens, of course. Now to move the slider, I need to go over here and click on the move there. To move that, nothing happens because there's nothing that's a function of that slider. But go down here, and I'm going to click. I'm just going to type in. Sorry, I'm going to type a point: cosine T, sine T. Cosine, and I want to say I need parentheses around the T. Yeah, cosine T, sine T, and the default, as far as I can tell, is that it calculates these in radians. And I'd have to double check if you ask me really quick how to change it to degrees. Maybe somebody knows, but I have to look that up. I don't deal with the degrees all that often. I'm just going to press enter, and it puts a point there. And you can see when T equals 0, then the point's right there. And when T equals about pi over 2, it goes up there to pi over 2. So that point's going to slide around the circle. Well, we need the other 3 points as well. So negative cosine T, sine T, that'll reflect it about the y-axis. So the 2 points will move in tandem when you do that. And then you want the see, cosine T, negative sine T, like that. And so they'll all 3 move, and the one more, both negative. Negative cosine T, negative sine T, like so. And then you can get them to move all at once. Now, the rectangle, one more point, sorry. We need 0, 1. 0, 1. So now the rectangle, for the 4 points, and also the triangles. Let's do the rectangle. So let's go to, I want to say polygon. If I just click there, let's see what other choices are. Regular, rigid, vector. Let's just go with plain old polygon. And I just want to click the 4 points in order, either going around clockwise or counterclockwise, maybe ABC. So click on the A, and then the B, and then the D, and then the C, and close it up back to the A. Okay, so what it does is it does well, at least 5 calculations. It gives us the links. It stores the links of all 4 side lengths. The 1.6 evidently is this one, which it gives a name of A, and this one down here, which it gives a name of D. Those are 1.6. And this one over here, it's calling B, that has a length of 1.2, and over here it's calling C1, that also has a length of 1.2. And it also stores the area. Evidently, if you multiply 1.6 by 1.2, you get 1.92. So that's the area of the quadrilateral. Now, if we wanted to display the area, we could right-click. So I'm right-clicking on the polygon and going to Object Properties. Right-click Object Properties, and For show label, you have various options. If you've given it a name, you can change the name to rectangle or whatever, or display that or not. For the value that it stores is the area of that rectangle. So I'm just click on value and showing the label. Click close, and it puts the 1.92 right there. Now that's kind of it's not in the best position, I guess. So what I want to do is right click on the 192, not click on it, but hold down there, and you can move the 1.92 to a better location, like right there. It's easier to see. Also the triangle. So let's try B, and then E, and then A, and then B again. I'm going to right click on that, go to Object Properties, Show Label, Value, and the area of the triangle currently is 0.32. And I think really all that's left to do is drag the value of t until we get them to be kind of close together. Now, I'll start with the value of t, and let's see what happens. Well, I kind of went past it, didn't I? What is it? Now, if what you'll notice is not too fast. Yeah, 0.78, 0.79. What can happen is that it's not as precise as you'd like it to be, because when I move the value of t, although the increment I set is 0.001, there are only so many values it can range through between 0 and 1.57. So I'm going to go to Object Properties and then increase the width of it to maybe 500. It makes it longer, but when you move it a little bit, it will take into account more values. Also, you can go rounding, basic things. Let's see. Options, rounding, 3 instead of 2. And let's see how close we can make those areas together. That's probably as close as I want. 0.783, 0.784. Almost had it. Should have brought a mouse. One more. Okay. So we could calculate then. Oh, well, it also stores. What was the original question? What's the value of h? So for the value of h, that is the height of the rectangle. We could go there, right-click on it, and click on Object Properties, Show Label, Value, and it looks like what? Approximately 0.399, something like that. For the area of the rectangle and the area of the triangle to be about the same. Now, there's not a lot of math there. That's just a number crunching, really graphical approach to this. But you can see the power that a tool like this would have if it's a matter of getting something that will work as opposed to being able to justify your answer. So hopefully some of these ideas will help if you want to try something like this next time. All right. Let's do some calculus. The next homework has been posted. For some reason on mine, it's saying that the homework problems cover the sections 2.2 and 2.3. We've done those sections, so they begin with 2.4, 2.5, 3.1, and 3.2. They're there as well as the solutions. Solutions actually get it right, 2.4, 2.5, 3.1, and 3.2. So if you want to print those and start working on them, that would be great. All right, maybe I should zoom out just a little bit. On this this first function that we look at, it's kind of a piecewise defined function on steroids. It's basically defined for the purpose of indicating 3 common ways. I say three primary ways. There's another way involving a vertical asymptote that's not mentioned here. The 3 common ways that a function can fail to be continuous at a point. Loosely speaking, a function is going to be continuous on an interval if we can draw the graph without having to pick up the marker or pen, whatever we're drawing with. But we want to be as specific as we can in terms of the idea of limit what we mean by a function being continuous at a point. Once we're clear on that, we can extend that to an idea of a function being continuous on an open interval, and then we can extend it to what does it mean to be continuous on an interval, a closed interval, or half-open interval that contains one or both of its endpoints. So we'll work our way there. So if a function is defined, well, we've got it. We've got it here. I'm not going to try to graph it. I'm going to accept the graph that we have here pretty much as given. And let's see if I can get enough of it to comment on it. I think probably I can. Here goes. So the three numbers, which are either in the domain or really close to being in the domain, I cut them off, but I think maybe I can put them back. No, there they are. So interested in what's going on or what's going wrong at 3, what's going wrong at 7, and what's going wrong at 9. When you have a function handed to you and it's defined as a piecewise function, typically that's what you look for, where these breaks are in the way the function is defined. It's defined one way to the left of 3, and then a different way to the right of 3, but to the left of 7, and then a different way to the left of to the right of 7, but then to the left of 9. So what's going on, what's going wrong at 3? Many ideas why this function? I claim it's not continuous at 3. Well, why not? There's a hole in the graph. The function is not defined at 3. F is not, let's say it like this, f of 3 is undefined. F of 3 is undefined. That's one common way a function can fail to be continuous. It can fail to be defined at a particular number that we're interested in. In fact, we can't even say 3 is in the domain of this function because f of 3 does, well, I hate to use the word does not exist. We kind of reserve that terminology for the idea of limit, but it's simply undefined. So that's one way a function can fail to be continuous. Well, not the same sort of issue here at 7. At 7, it is defined. What is f of 7?
4.
It's 4. We could get that one of two ways. We could say, well, let's see, this is the interval we need to look at if we want to figure out what f of 7 is, because 7 is between 7 and 9 inclusive of the 7. 7 minus 3 is 4. Or we can look at the graph and see there's a dot right here on the graph at the point 7, 4, and that must mean that f of 7 equals 4. So sure, f is defined. F of 7 is defined, but it's not continuous at 7. Why not?
Because you have to pick your pencil up.
You have to pick your pencil up, exactly. Basically, we're going along just like that. Can you see that? Yeah, we went along this like, and then we have to jump all the way up there instantaneously. A little bit later, we'll call this an example of a jump discontinuity and make that term as official as we possibly can. But because even though it's defined, the limit fails to exist, the limit of f of x as x approaches 7 fails to exist. We say there's a discontinuity. This function has a discontinuity at 7. It's not continuous at 7. So 9. Getting better, I think. Is f of 9 defined?
Yes.
It is, yes. What is f of 9?
3.
F of 9 is 3. So f of 9 is defined. What about the limit of f of x as x approaches 9? Does it exist? Your best guess based on the picture there. As x approaches 9 this way, the y values appear to be approaching 6. And as x approaches 9 from this direction, the y values also appear to be approaching 6. So I'm thinking, as x approaches 9, f of x approaches 6. So it looks like this limit exists. So the function is defined, the limit exists. Is it continuous at 9? I claim it's not. Why might I think it's not continuous at 9?
Because you've got to pick your pencil up.
You do have to pick the pencil up to jump over the hole. Now, I'm not going to call this one a jump discontinuity because it's basically just a hole in the graph. This one, as well as this first one over here at the point A that we talked about, are going to be called removable discontinuities. It'll be called a removable discontinuity if the only thing that has to be done to remove it is to define or redefine the function at that number. So here, f of 9 equals 3. If we had the liberty to redefine the function at 9 to fill in the hole, what should we define it to be? 6. If we scratch this out and fill in the dot instead and say f of 9 equals 6, not 3, that would remove the discontinuity. So I don't know, it might not be our function, we might not be at liberty to do such a thing, but if we could, that would do it. So I'm going to leave the hole in the graph there and simply say this, and I'm going to leave this unscratched out. Functions defined, the limit exists, but as it stands, the limit of f of x as x approaches 9 does not equal what the function is defined to be at 9. And that causes the function to be discontinuous at 9. So it'll remedy all three of these if I can just change this not equal to an equal to. If I could just fix that. Because if for some way I could erase that not equal to bar, then kind of look what I'm saying here. I'm saying the limit exists, I'm saying the function is defined, and they're equal to each other. That's what we mean when we say a function is continuous at a point. So let's look at the official definition. And I got to close a lot of this. How about this? And this. And this. There we go. So here's the official definition, but it's going to be good if we just have, one more try, just have the third item on the list. That's going to be enough. The function has to be defined in order for that function to be continuous. If it's undefined, you've got a discontinuity at C. The limit has to exist. If the limit doesn't exist, whether it's a jump or whether it's a vertical asymptote or whether it's some kind of crazy oscillating thing going on, if the limit fails to exist at C, the function is not continuous at C. If the function is defined and the limit exists, it has to be defined to be the value of that limit. They must agree. The value of the limit and the value of the function must agree. If they do, then it is continuous. Now suppose we drop the first two and we just say the limit of f of x as x approaches c must equal f of c. Sometimes it's easier to remember one thing than it is to remember three things. If you could just remember this as a definition of continuity at a point, this, I believe, will suffice. Because if this is true, that means, number one, the function is defined. If you can actually talk about f of c on the right-hand side, it means number one is satisfied. And number two, the limit must exist in order for it to equal f of c, so that covers number two. And then three, well, that's three. So if you just take statement 3, that's the definition of continuity at a point, at a particular number c in the domain of a function. The extension to an open interval is almost immediate. If we've got an open interval and we're wondering whether or not the function is continuous on that entire open interval, basically pick a c, any c in that open interval, this has to be satisfied. And if that definition is satisfied for every number in that open interval, then we say the function is continuous on that open interval. Otherwise, we enumerate the discontinuities that it may have on that open interval. A little bit more going on when we talk about to try to include either one of the endpoints to make it half open or closed, but we'll get to that. Sometimes the interval we're talking about is the set of all real numbers. If this definition holds for every value of x in the set of, every value of x, every real number, then we say it's everywhere continuous, or sometimes I'll say continuous everywhere. It's continuous on negative infinity to positive infinity. I think I've got another copy of that, so I'm going to click Don't Save. Just get out of GeoGebra. Whoa! Cancel. Already got out of GeoGebra. There we go. So examples 1, 2, and 3 are kind of related, so we'll work our way there. Examples 1 and 2. F of x equals x plus 4 times x minus 3, all over x minus 3. I've gone ahead and factored the numerator. A lot of times you'll see this problem, and the numerator will be, what, if I FOIL that in my head, x squared plus x minus 12, and then you just have to factor the numerator and realize that x minus 3 is a common factor to both the numerator and the denominator. Is it continuous at x equals 3?
No.
Yeah, we could start by asking ourselves, what is f of 3? 0 over 0, it's undefined. So nope, f of 3 is undefined. Okay, so that's an easy one. Now, if you consider the graph, if you're sketching the graph of this, the graph is almost the same as y equals x plus 4. Because when you simplify it, you scratch out the x minus 3's, and that's basically what's left, y equals x plus 4. The only difference between the graph of this function and the graph of y equals x plus 4 is that the hole in the graph. Yeah, y equals x plus 4 doesn't have any holes in it, but this one has a hole with an x coordinate of 3. So if I'm going to graph it, I would graph, let's see, 1, 2, 3 for the y-intercept, and I think the x-intercept is over here somewhere, and at 1, 2, 3 this way, oh sorry, got my 3 in the wrong place. The y-intercept is 4, isn't it? There, that's better. I'm sorry about that. Looking at the 3 and thinking the wrong thing. So right up in here, there is a hole in the graph because at 3, it's undefined. So that's kind of what the graph of our function looks like. It's fairly easy to graph. Just put a hole that has an x-coordinate of 3 when you get there. Now example 2, not much more difficult to graph because it's defined using the same expression. If x is not 3, and if x is 3, it's equal to 5. So there's 4 right there. There's 5 right there. That's the point. 0.35. Is this continuous at 3?
Yeah.
No, it's not continuous at 3. The limit exists. If you were going to evaluate the limit of this expression as x approaches 3, you would scratch out the x minus 3's, and you would substitute 3 for x in the expression x plus 4. You say 3 plus 4 is 7, and that's not equal to 5, though. So the limit exists, and it's not equal to what the function is defined to be. So the limit of f of x as x approaches 3 equals 7, but f of 3 equals 5, so it's not continuous. So h is not continuous at x equals 3. Is this a jump discontinuity or a removable discontinuity? Removable? Let's remove it then. We look at example 3. Example 3, it was not good to define the function to equal 5 at 3 because the limit was equal to 7 as x approaches 3. So it would be better if we define f of 3 to equal 7. Yeah. So there we go, just like that. Let me go back to a friendlier color there. The dark blue. 7. Now, that fills in the hole. If we're graphing this, 1, 2, 3, 4, and over like that, where previously there had been a hole at the point 3, 7, that fills it in. So now, the graph of this function is identical in every way, including the point 3, 7, to the function h of x equals x plus 4. Absolutely no difference between them. Same domain because we've defined it at 3. That was the only discrepancy. So this is just a ridiculously fancy way now of saying exactly the same thing as that. The two functions, and it's appropriate to give them the same name. It's h in both cases. Filled in the hole. We remove the discontinuity. So h is continuous, in particular, at x equals 3. And as we'll see in the not too distant future, since it's a polynomial, it's continuous everywhere. Polynomials are going to be nice. They're continuous on the set of all real numbers. I'm so sorry about that. That's making you dizzy. I didn't mean to do that. All right. We're going to need to be talking about the idea of one-sided limits, because in many cases the limits will fail to exist, and we want to be able to describe precisely why they're failing to exist. A lot of times they'll fail to exist because as x approaches a number from one direction and as x approaches a number from another direction, the function values may approach different values. What we'll see is the pieces need to meet in the middle in order for the limit, what we'll call a two-sided limit, to exist. And when they approach different values, we want to say that each one is a one-sided limit that exists, but if they don't agree, the two-sided limit does not exist. So definition, let f be a function defined in an interval extending to the right of c. Maybe hard to see right here. I want to say the limit of f of x as x approaches c, and I put a little superscript of a plus here. X approaches c from the right is how we read that. Now, as far as the picture goes, if I say that's equal to L, and look to see what's going on for my function, typically we would think of c as being maybe, well, the left-hand endpoint of an interval where something interesting is going on. So I'm going to put c right here, and maybe an open circle right there. Maybe the function is defined at c, maybe it's not, but perhaps it looks something like that. And as x approaches c through values that are greater than c, so we mean from the right, that through values that are greater than c, and the y values, as that's happening, are approaching L, then we say the limit of f of x as x approaches c from the right equals L. Now it may be that something else is going on altogether from the left. I mean, from the left it might be completely erratic behavior, or it might be approaching some different number, or it might actually be approaching L. But that's kind of the picture that we see. Let's see, do we want to explore the deltas and epsilons? I don't know if we do or not, but let me make sure my definition makes sense, and then maybe we'll leave it at that. Basically, it says for each epsilon greater than 0, so we're thinking L plus epsilon, L minus epsilon, L plus epsilon, L minus epsilon, and the horizontal lines that go with it. Let's go with red horizontal lines. Right there, and right there. There exists delta greater than 0. I'm thinking the delta probably would need to be, if I go to this point where this horizontal line intersects the function, if I scoot a little to the left of that, maybe I'll have a delta that works. So maybe this is the c plus delta. Oops. Yes, that's the c plus delta that I should have been referring to if we're approaching from the right. As long as x is between c and c plus delta, that is to guarantee us that the function is between L minus epsilon and L plus epsilon. That is, f of x minus L has absolute value less than epsilon. So if I had the liberty of doing so, I would replace this and this. Those should swap places. So here should say x is between c and c plus delta. X is approaching c from the right, so we're considering values a little bit greater than c. And here, x is between c and c minus delta. Not likely that I'm going to ask you to pull out the epsilons and deltas on the next test, so no worries there. I just wanted to make sure this definition was at least correct, and sadly, it was not. So we can fix it though. X approaches c from the left. Let's say there's c, and x is approaching c from the left. As x approaches c like that through values that are less than c, if we look at the corresponding points on the graph, then they're going to be approaching this number L. So if we look at L plus epsilon, and L minus epsilon, and extend these horizontal lines like this and like this, okay, that's kind of a key point there. I want to choose a delta, maybe right here, and call that c minus delta. Just want to be sure that for any epsilon, any positive epsilon, there exists a delta such that if I'm anywhere in here, x is between c minus delta and c, then I evaluate the function and I stay within the horizontal red lines. That's what we're saying there. Visually, if I say it's approaching L it's approaching C from the left, the graph needs to be approaching that point on the graph that has a y-coordinate of L. That's what we mean, and that's the way we'll interpret this in the applications that we'll see. And we'll begin with this one. Example 4, and eventually the concentration of piecewise defined functions won't be quite as great, but this section, just due to its nature, lends itself to lots and lots of piecewise defined functions. So hopefully, if piecewise defined functions aren't your favorite things in the whole world, the quantity of them will diminish in upcoming sections. So don't sweat them too terribly much. Just provide for good examples. So we have a function that's defined to be x plus 1 if x is greater than 2. Consider what the graph would look like of the entire line y equals x plus 2. Don't draw this on your paper, but, y equals x plus 1. If we were to extend this, y equals x plus 1 looks kind of like that. So what we want is just the piece of y equals x plus 1 that has x values greater than 2. And that's the piece that we see. If we were to extend y equals x minus 1 all the way from the left to the right, this is y equals x minus 1. You see the y-intercept there. And if we were to extend that, that's what the graph of y equals x minus 1 would look like. But we only want the points on that graph that have x coordinates less than 2. So we erase all of that, and then we only have points with x coordinates less than 2. What is f of 1? Sorry, f of 1 is 0. that was a dumb question. That was an irrelevant question. Not a dumb question, but just irrelevant. What's f of 2? That's a better question. I guess we have to ask, is 2 greater than 2 or is 2 less than 2? Yeah, none of the above. We need an or equal to bar next to one of these. So f of 2 is undefined. That's okay. We don't need the function to be defined. We need the function to be defined if we're hoping this will be continuous at 2, but clearly it's not going to be continuous at 2. But we don't need it to be defined to explore the limit. The limit is not determined by how the function is defined at any one point, but by how it's approaching a particular number along an interval to the left or to the right of that point. So we want the limit of f of x as x approaches 2 from the left. So from the left, we're considering values of x that are less than 2. So from the left, if we look at the picture, it's going to be like this as x, let's see, as x gets really close to 2 from the left, then the y values of these points along here are really getting close to what number?
1.
Getting close to 1. This is the point 2, 1 on the graph. So the y coordinates, the points are getting close to the point 2, 1. So the y coordinates of those points are getting close to 1. So that's equal to 1. Now in practice what we'll do is this. To evaluate this limit algebraically by direct substitution when possible, we'll just say, okay, we only want to consider values of x that are less than 2, so we're only going to consider this rule. So the limit of f of x as x approaches 2 from the left is equal to the limit of the expression x minus 1 as x approaches 2 from the left. Because all along in here, as we're to the left of 2, this is a piece of the line y equals x minus 1. So we can use that algebraic expression to calculate the limit, even though there's more to the function as a whole than that algebraic expression. To the left of 2, that's all we really care about. So we can use that expression. So we substitute 2 for x, and 2, oops, I don't need that other parenthesis, sorry. 2 minus 1 equals 1. For this one, the limit of f of x as x approaches 2 from the right. Well, visually, what's going on? Visually, x is approaching 2 from the right. Points on the graph are approaching what point?
3.
So the y coordinates are approaching 3. Yeah, so looks like that's 3. If we didn't want to draw the picture or think about such things, we could look at the rule and say, okay, from the right, that's values of x that are greater than 2. So if x is a little bit more than 2, then the function is going to be defined using the expression x plus 1. So the limit of f of x as x approaches 2 from the right is equal to the limit of x plus 1, or I should say x plus 1 as x approaches 2 from the right. So 2 plus 1 equals 3. So to evaluate the limit, we use the expression that's used to define the function on the interval that we care about. And the interval that we care about is x's that are greater than 2. Now, as we approach from the left, it's approaching 1. As we approach from the right, it's approaching 3. What can we say about the limit of f of x as x approaches 2? Not the one-sided limits, but the two-sided limit. I just ask you, what's f of x getting close to as x gets close to 2?
1 and 3.
1 and 3. You almost have to say it depends. It depends on whether we approach from the left or whether we approach from the right. And for limits, we have to give a definitive answer. It has to be approaching a single number, and this one is not. So this limit does not exist. Does not exist. For capital D and E, I don't know why I went with lowercase d and e there. This limit does not exist. So what we need is for the pieces to meet, the pieces of the graph to meet at that particular value of x at 2 in order to make the two-sided limit exist. This one done. Now example 5, my whole point in this example is a lengthy example. I'm going to try to make it as short and sweet as possible. my whole point in this example is that the values of the two-sided limits, values of each one-sided limit have nothing at all to do with how the function is defined at the number 1 that is interesting here, the number 1 where it's in between. So the first function, it's completely undefined at 1. The second function, it's defined to equal 2 at 1. And the third function, it's defined to equal 1 at 1. And my point here is that we'll evaluate the limit as x approaches 1 from the right, as x approaches 1 from the left, and find that they're the same for all three functions. Now, left and the right are not the same, but for f, for g, for h, if we just consider either the one-sided limit or the either from the left or from the right, those are going to all agree with each other. So let me see if I can make the point as succinctly as possible. First function, and we'll consider the graph here, or we can just plug in the 1 if you'd like to. As x approaches 1 from the right, we look and see where is x a little greater than 1. Greater than 1, it looks like it's defined to be negative x plus 4, so this is going to be the limit as x approaches 1 from the right of negative x plus 4. And that's going to be, substitute the 1 for x, and that's what? 3. Visually, as x approaches 1 from the right, points on the graph are approaching a point whose y-coordinate is 3. So the y-coordinates of those points are approaching 3. So the value of the limit is 3 as we go from the right. What do we go from the left? This equals the limit as x approaches 1 from the left of that other rule, x, when x is a little bit less than 1, to the left of 1, it's defined by the expression x. So this equals what we get when we take 1 and substitute it for x, and that's 1. So as we're approaching from this direction, the point there is the point 1, 1, so the y-coordinates are approaching 1. Now, it will belabor the point unnecessarily if I repeat a lot of that. So basically, what I'm saying in the other two examples, the limit of g of x as x approaches 1 from the right, because we're approaching the point, and I should go with an open circle there, 1, 3, that's equal to 3. Here the graph is approaching the point 1, 1, so that's equal to 1. Doesn't matter that g of 1 equals 2. Limit doesn't care how the function is defined at 1. It's what's it approaching. Same thing here. The graph is approaching the point 1, 3. So as x gets close to 1 from the right, value of that limit's equal to 3. Here the graph is approaching the point 1, 1. So as x gets close to 1 from the left, y-coordinates are approaching 1, so same thing. Now the function happens to be defined to be 3 there, but the limit doesn't care. It's unaffected by that. So 3, 1, 3, 1, 3, 1. And of course in all three of those cases, even though it did not ask, the two-sided limit fails to exist. Let's see. Okay, good. Example 5. Let's see if we have something new here. Not really new. I think hopefully this will be an easy example. Using two different linear expressions to define this function. It's defined to be y equals x plus 1 if x is less than 1. If I were to draw the entire graph of y equals x plus 1, of course it would look like that, but I don't want the entire graph. I just want points that have x coordinates less than 1. And those points that have x coordinates less than 1 are on that piece of the graph. The other one, negative x plus 3. If we were to draw the entire graph there, negative x plus 3 would look something like that. y equals negative x plus 3. But of course, we don't want the entire graph of that. We just want the piece of it that has x coordinates greater than 1. So erase, erase, erase. Yeah, that's the portion of it we want. I could extend it, actually maybe a little bit more down here, just so it doesn't give the impression that it stops. Now we do need that much, but here we go for our function. As x gets close to 1 from the left, so we approach 1 from the left, the graph itself is approaching the point 1, 2. So the limit of f of x as x approaches 1 from the left equals what?
1, 2. Or 2.
Well, it's the y coordinate there too. As x approaches 2 from, x approaches 1 from the right, points on the graph are approaching the point
2.
1, 2. So the limit of f of x, the orange showing up, yeah, it's okay, as x approaches 1 from the right is also equal to 2. So both one-sided limits exist, and they agree. What does this mean?
That it has a limit.
That the
It's a double-sided.
double-sided, two-sided limit, the limit, same limit that we talked about all the way up to today. The limit of f of x as x approaches 1 exists, and also equals 2. So you could say, if I ask, as x gets close to 1, what does f of x get close to?
2.
And you could say 2. You don't say, well, maybe 1 if you approach from this way, and 3 if you approach from the other way. You can just say 2. It gets close to 2. No picture is provided for this one. Youch. I have to stop and think about this one a little bit. Should we try to draw the picture, or try to do it? Maybe we should try to do it without the picture. You think? Maybe without. Let's try it without the picture. If that doesn't work, then we'll try to draw the picture. This function looks like it might be undefined at 0 and undefined at 4, and maybe some other places. Who knows? But hopefully, as x is close to 0 and is close to 4, we can be able to evaluate it and then evaluate these limits. Consider what happens as x approaches 0 from the left. Suppose x is a little bit less than 0. A little bit less than 0, approaching 0 from the left. Function values, if I want to find f of -1, for example, which rule would I use to evaluate f of -1? The top one. That's where x is a little to the left of 0, a little less than 0. So what we can do is say the limit of f of x as x approaches 0 from the left is equal to the limit of the expression x squared minus 1 as x approaches 0 from the left. Now once we have the expression x squared minus 1 there, although the function itself might just have a piece of that parabola, when we evaluate the limit, we can feel comfortable using the entire parabola because we're approaching from the left. So it's a polynomial. Polynomials are nice. We can evaluate the limit by direct substitution. Just substitute 0 for x. It's -1. There we go. Really don't need a picture to do this problem. Now, the limit of f of x as x approaches 0 from the right, we have to say, okay, suppose x is just a little to the right of 0. What rule would we use to evaluate the function? The middle one. We would use this. 0 is a little to the right, so I guess I should be the whole thing there. Use the x minus 2. So this is equal to the limit the limit as x approaches 0 from the right of x minus 2. That's a polynomial. So we can evaluate this limit by direct substitution. Just plug in the 0. And that evidently is equal to -2. Now when we get to the two-sided limit, I know the print is small, but there's no plus or minus superscript there. We just need to know this. Does the limit as x approaches 0 from the left exist? Yes. Does the limit of f of x as x approaches 0 from the right exist? Do they agree?
No.
No, and I'm going to put it right this way or this way. They don't agree. One is approaching the point 0, -1. The other one's approaching the point 0, -2. So the two-sided limit does not exist. If I ask you, what does f of x get close to as x approaches 0? You have to say it depends. It depends on the direction from which we approach 0. So this, again with the lowercase d, does not exist. So even though the two one-sided limits both exist, they do not equal each other. More of the same. X approaches 4 from the left. If x is a little less than 4, well, x is between 0 and 4. So we use the expression x minus 2. And so this is the limit of x minus 2 as x approaches 4 from the left. And that's going to be 4 minus 2, which is 2. If x is a little bit more than 4, then we use this one. So it's the limit as x approaches 4 from the right of the square root of x. Upcoming example will involve a radical like this, but this is going to be the square root of 4. We had a theorem about limits. Limits of a radical of an expression is a radical of the limit of the expression. So that's the square root of 4. We can use direct substitution and get to, hey, the two one-sided limits both exist, and they equal the same value.
So it's double-sided.
So it's double-sided, and it equals 2, just like that. Example 7, we want to find the limit of the square root of 9 minus x squared as x approaches 3 from the left. What does the graph of y equals the square root of 9 minus x squared look like? What does that look like? Just a quick visual, some shape or something. If we look at y equals the radical and then we square both sides, we'd have y squared equals the square of the radical. So y squared equals 9 minus x squared. A little more familiar without the radical. If we add the x squared to both sides, we get x squared plus y squared equals 9, which is what? It's a circle. Yeah, so if we were to graph the entire circle, what is the radius length of the circle? 3. So the top half of the circle would look something like this, and the bottom half of the circle, would maybe look something like this. Now when we write y equals, clearly this is not a function, this fails the vertical line test in a lot of places. We write y equals the square root of 9 minus x squared. We're only talking about the principal square root, the positive square root. So the y coordinates have to be greater than, or maybe in a couple of cases equal to 0. So the graph of the function itself, y equals the radical there, does not include the bottom half of the circle. It's just the top half of the circle. But it agrees with x squared plus y squared equals 9 for all those points on the graph. So this is kind of what it looks like. As x approaches 3 from the left, well, in this case we have to say x approaches 3 from the left because it really can't approach from the right. Because if we try to approach from the right, the function is undefined at 3.1 and 3.01 and 3.001. It doesn't make sense to approach from the right. But as we approach from the left, we can see as we approach from the left, points on the graph are approaching this point right here. So their y coordinates are approaching 0. We can get this by direct substitution. This is going to be the square root of 9 minus 3 squared, which is the square root of 0, which is 0. Now we can say this function is continuous, how to say this? The limit as x approaches 3 from the left exists, but we really can't talk about the limit as x approaches 3 from the right. So what about the continuity at 3? There's not really a situation where x is approaching 3 from the right and something bad is happening, it's just not approaching from the right. So this is a situation where we'd like to be able to indicate that f is continuous on a closed interval. Certainly f is continuous at any point between -3 and +3, just by the nature of the graph, and no holes, no jumps. And we have a radical and a polynomial, and they behave pretty well as long as we're choosing numbers in the domain of the expression. So we want to be able to say something about the continuity of a function on a closed interval. And here's what has to happen. For a function to be continuous on a closed interval, AB, it has to be first continuous on the open interval, AB. So if we've got our function, and there's A, and there's B, I'm going to draw a portion of the graph like that. This pretty much has to happen, and this is the graph that we would have if we say the function is continuous on the open interval AB and has hope of being continuous on the closed interval. Because by drawing the graph where it's actually approaching a particular point, rather than having a vertical asymptote, rather than being some kind of crazy oscillating infinitely often behavior, the limit, because it's behaving well there, the limit of f of x as x approaches a from the right equals, well, it exists, and we need it to equal f of a. Now, I don't have an f of a on here, so if I want this to have hope of being continuous on the closed interval, I don't want the dot here, I don't want the dot here. I want it to be what that value of the limit is going to be, f of a. So erase that one, erase that one. I want to fill in the dot if this is going to be continuous on an interval that includes that a as the endpoint. Likewise, this limit of f of x as x approaches b from the left exists because as x gets close to b from the left, we're approaching a point. And now we want the function to be defined to be, whoops, missed it. Oh, that was unfortunate. Come on. Wow. Am I going to miss it again? Maybe. F of b. We want it to be defined to equal f of b. So basically we need a solid dot at A, and the graph needs to be approaching that solid dot. We need a solid dot at B, and the graph needs to be approaching that solid dot. And then we can say the function is continuous on the closed interval, including both endpoints A and B. Now, there are situations where it might look like this. And then what we would say, there's A, there's B, F is continuous on this half-open interval. We can include the A because it's approaching the dot, the solid dot at A, but at B, it's approaching the wrong dot. It's approaching the open circle instead of the solid dot, so we cannot include the B in the interval where it's continuous. So we could do it, and we could put the open circle at A if we wanted to, and the solid dot at B, and include the B and not the A. Here's kind of an important point that I need to bring out here. Suppose that we have a function, and there's A right there, and it's doing this, and then it's doing this, and let's say it's doing this, and we've got b over here. Can we say the function f is continuous on the closed interval AB?
No.
Well, here's the thing. When I guess I'd taken this course many years past, and I started teaching the course, it seemed like a contradiction because you can look at it and see it's not continuous at A, is it? Right? It's not continuous at A. There's a jump right at A. But here's the thing. In order to be continuous on a closed interval that contains A as a left-hand endpoint, it doesn't have to be continuous at A. It just has to be continuous from the right at A. That's all that has to happen. Yes.
Wouldn't that be because technically there's a limit there on as approaching from the left, meaning that it isn't actually at A? It's just infinitesimally close to it?
Well, the limit.
Technically, it's not actually A.
Yeah, as it approaches A from the left, that limit does exist. The limit of the function as x approaches A from the left exists, and
the limit exists, but the actual number doesn't quite.
Well, it's defined at A. F of A is whatever this number up here is.
Yeah, I know. I meant along the line from the left.
Oh, from the left? Yeah. Well, I guess I'm trying to draw this as so that it fails to be continuous just as badly as possible. Maybe I could have gone with the vertical asymptote, but this is kind of a classic example of a function that fails to be continuous at A. It's just misses it by this much. It fails to be continuous at A, but it's continuous on the closed interval that contains A as its left endpoint, because it's continuous from the right at A, and it's continuous from the left at B, and it's continuous on the open interval in between, because even though I might have picked up the marker, I'm not sure, you can get from A to B without picking up the marker. So it is continuous on the closed interval, even though it fails to be continuous at one of the endpoints. And that feels kind of weird. It felt kind of weird the first time that I made that observation, and I thought, is that really right? And it really is. Example 8. This function whose picture we drew just a moment ago is continuous on what interval? It's continuous on that closed interval from -3 to 3. Basically, for this to happen, it has to be continuous on the open interval from -3 to 3. And it is because it's all that's in the domain, and it's a radical function composed with a polynomial function. So there's no reason to believe it would not be continuous, have any holes or vertical asymptotes or jumps in there. And it's continuous from the right. Let me just look back at the picture. It's continuous from the right at -3 because the graph is approaching the point where it's defined to be there. And it's also continuous from the left because the graph is approaching the point that has that limit as its y coordinate. So it's continuous on that closed interval.
And we'd have had to graph that if we hadn't already, right? We'd have to graph
it
it
would
right now.
It would probably be helpful to graph that. Otherwise, there would be a lot of writing stuff down. Basically, you'd have to say everything that I said. F is continuous on the closed interval. F is continuous from the right, and you would have to justify that by evaluating the limit as x approaches 3 from the right, and also -3 from the right, and also evaluate the limit as x approaches +3 from the left. But I think we kind of did most of that in a couple examples ago, so I skipped the picture, and I feel the clock ticking. Example 9. I think I'd like to draw this picture, and just see if we can inspect the graph and get it. The graph of y equals x plus 1 is not too tough, but I just want the portion of the graph in between -2 and 3. -1, -2, 1, 2, 3. And how high does it go? Not too high. So it goes to the point 0, 1, and 1, 2, up to the point 3, 4. And then down here it goes as low as the point -2, -1. Okay, that's the middle piece. The piece on the left, f of -2 equals what? 5. So that's point -2, 5. And f of 4 equals what? Okay, my fault for asking the wrong question. I won't fault you for giving. I mean, I guess you should have said undefined and just looked at me like I'm stupid, because I sort of was. F of 3 is the question I needed to ask. What's f of 3?
4.
4, yes. We were all thinking the same thing, it's just didn't work out so well. Okay, f of 3 equals 4, so fill in that solid dot. Discuss the continuity of this function. Well, here's what I'd like to do. Break it down a little bit like this. First, let's consider the open interval. Is f continuous on the open interval? Now, we might be able to say more than this, but can we say at least this? On the open interval from -2 to 3. I mean, it's going to turn out we can include the 3 in addition to this, but it is continuous on the open interval. There's just nothing bad going on. It's equal to a polynomial. Polynomials are equal to the values of their limits, so it's all good on the interval from -2 to 3. Is f continuous from the right at x equals -2? As x approaches -2 from the right, are the points on the graph approaching a point that has f of -2 as its y coordinate? Well, they're approaching a point that has -1 as its y coordinate, so that limit exists, but it needs to equal 5 if it's going to be continuous. So the limit of f of x as x approaches -2 from the right equals -1. But sadly, that's not equal to 5, which is what f of -2 is. Bummer this. So we cannot include the -2 in the interval where this function is continuous. Is f continuous from the left at x equals 3? Yes, it is. The limit of f of x as x approaches 3 from the left equals 4, but that's also equal to f of 3. There we go. So that's a yes. I guess I didn't answer the previous question. Although this one was a yes, the previous one was a no to this question. So what can we say? F is continuous on the half-open interval that extends from -2 to 3, and includes the 3, but does not include the -2. Because up to the right, it goes to the solid dot. Down to the left, it goes to the open circle. Properties. What types of functions are continuous? Well, these properties of continuity turn out because the definition of continuity is tied so closely to that of the definition of limit. Properties that we looked at for limits are very similar to these properties involving continuity. If we have a function, y equals f of x, and it's continuous at a number, if we multiply that function by a non-zero constant, or certainly if we multiply it by 0 even, that function too is going to be continuous at the number c. It's a little bit more challenging to show, but if we have two functions f and g that are both continuous at c, the new function f plus g is also continuous at c. F minus g is continuous at c. Fg is continuous at c. And the quotient is continuous at c, provided the denominator doesn't equal 0. If the denominator equals 0, then there may be a vertical asymptote at c, but it will not be continuous there. Examples of functions that are continuous, but which we're not going to take the time, since it's not an advanced calculus course, it's just a Calc 1 course, so no worries with excessive epsilons and deltas for such things. Polynomials, rational functions. Now, notice every point of their domains. Now, you know a rational function, if there's a number that makes the denominator 0, is not going to be continuous everywhere, but it's continuous everywhere that the denominator is not equal to 0. So every number in their domains is what it says. Radical functions often are missing a lot of numbers from their domains, but if it's in the domain, it's continuous there. And trig functions, sine and cosine, are continuous everywhere because they're defined everywhere. But the other four trig functions have vertical asymptotes every so often, and they'll be continuous everywhere except where those vertical asymptotes occur. Exponential and log functions. Exponential functions are defined and continuous everywhere. Log functions, you know, you don't want to take the log of 0. Don't want to take the log of anything negative. You got to keep it positive with logarithms. But everywhere in the domain of a log function, we'll find that they're continuous. It's kind of a broad, sweeping statement, but there it is. Example 10, maybe time for this one. 10a, we've got a rational function. It's continuous everywhere except where? It's not continuous at 7. Anybody know what's going on at 7? There's actually a, I'm going to take our time with this or consider the graph. If x is really close to 7, the denominator is really close to 0, but the numerator is really close to 10. And 10 divided by a really tiny number could be a gigantic positive number or a gigantic negative number, depending on tiny on which side, small positive or small negative number. So the graph is blowing up at x equals 7. The graph, let's see, I guess the picture might be good there. 1, 2, 3, 4, 5, 6, 7, 8. Vertical asymptote there. If x is a little bit, we'll talk about infinite limits next time, and see ways of quickly deciding is it a positive infinity or negative infinity. If x is a little more than 7, over here to the right, then 7 plus 3 is going to be a little more than 10. 7 minus 7 is going to be a little more than 0, making it positive. And a number close to 10 divided by a small positive number is going to be a great big positive number. So the graph is going to approach positive infinity, because it does like that. On the other hand, if x is a little less than 7, the numerator is going to be a little less than 10, but the denominator is going to be a tiny negative number, and you divide a positive number by a tiny negative number, you get a great big negative number, so it's doing like this. What we'll say, and this might be as good a place to stop as any because it's a nice segue into what we'll eventually get to next time. This is a case where the limit as x approaches 7 will fail to exist. The two one-sided limits, one of them we can call positive infinity, the other one we can call negative infinity, but even that will not say that they exist, but simply will describe the manner in which they fail to exist. So there's a vertical asymptote at 7, but it's continuous everywhere else. So continuous on negative infinity to 7, and 7 to infinity, vertical asymptote at x equals 7. Okay.